Okay, 7/8's the last section we're going to do in Chapter 7, and it's on improper integrals. Just to keep you up to date on the schedule, we're going to talk about this Wednesday, and then Friday we'll start reviewing, Tuesday we will continue reviewing, and Thursday of next week will be our first chapter test. So 7/8 is integrals where there's a problem with the limits of integration. In this case, I have 0, and you can already see the problem here, I hope, is infinity is at the top of this integral. And the fundamental theorem says that we can take this antiderivative and plug in the bottom number and plug in the top number, subtract those two, but that requires that they both be real numbers, and infinity is not a real number. But I think you understand what it's implying. It's trying to find the area under this graph, which is e to the negative x here. How much area is that from 0 and going all the way out to the right? And you might just say, well, that's never-ending area. It's got to be infinity. But sometimes areas like that will actually not ever go over a finite amount. It's like adding up an infinite geometric series. Sometimes those series converge, sometimes they diverge. So we can actually keep on adding on area infinitely and never go over a certain amount, and we would say that it converges to that area. So here's how we're going to deal with these. You can't just leave 0 and infinity on there and then substitute them in after you've taken the antiderivative. Instead, what we have to do, just to be, as I like to call it in this section, politically correct, because really we all know that the infinity is there and we're just going to plug it in at the end. But because it's improper to leave it there, we write something like this. We're going to take the integral from 0 to b, and then we're going to let b approach infinity. So you can't technically sub in an infinity, but you can sub in a b and then see what happens as that b gets really, really, really big. Okay? So now we're just going to approach it like any normal integral. We're going to integrate it, sub in the b and sub in the 0, and then worry about the fact that it goes on forever. And this integral isn't too bad. It's just integral of e to the u. U is negative x, then du is negative 1 dx. So I just need a negative inside and a negative outside to compensate for it. So I end up with a limit as b goes to infinity of negative e to the negative x evaluated at b and at 0. Okay, so now I can plug in my b and my 0, and I'm plugging in for x. Remember that those limits of integration are values of x. So I substitute in and I get the limit as b goes to infinity of negative e to the negative b minus negative e to the negative 0. Okay, and so these tend to cause a lot of trouble with the negative exponents on e's. Let me just figure out, first of all, this, I know it's negative, and e to the negative b on top is the same as 1 over e to the b. So I'm put that on the bottom and make it positive. And then I've got e to the 0, which is 1, minus negative is plus 1. All right? So now I have to see what happens to this as b gets really, 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 really big. Okay, as this b right here grows, the bottom of this thing gets really huge. And a huge number on the bottom is equal to a 0 overall. So this limit is equal to 1, because the first part turns to 0 and the second part is just a 1. And figuring out that negative 1 over e to the b is 0 is probably the trickiest part. People want to call that infinity. They want to call it lots of other things, but negative 1 over basically a million is 0. And as b gets bigger and bigger, it'll get beyond a million and closer to 0. So don't forget what this 1 represents. This 1 is the integral of e to the negative x from 0 to infinity. So what that means is my blue shaded in area right here will never go above 1. Right? I can extend it out as far as I want, and I will never get above 1. And just to maybe try to convince you that a little more, let's check it out on a graph. Okay, I'm going to graph e to the negative x, and see where my zoom is. Let me zoom in on that a little bit just to get a better picture. So here's the graph that I had drawn. And there's a couple ways you can find areas with your calculator. I'm going to do second calc and option 7. My lower limit is 0. And let's just say, what if I integrated up to x equals 5? And since 5 wasn't on my window, it's not going to let me do it. So let me change my window up to, let's just make it 20. My picture's worse, but it'll let me now evaluate the integral. So let me try that again. Calculate the area, option 7, from 0 to 5. And if I integrate just up to 5, my area is 0.99326. Okay, if I integrate from 0 to 10, now my area is 0.9999. Let me do one more just for good measure. Let's go from 0 to 19. My area should be all 9s. So you can see that this is converging to 1. All right, the area will never go above 1, and it will never stop getting closer to 1. So we would say that this definite integral converges to 1. Okay, and the fact that infinite things can add up to finite amounts is kind of a tricky idea, but you should have covered that in stats at some point, talking about infinite geometric series. And these are very connected to the series chapter that we're going to start in a couple of weeks. Let's look at another example that acts in a different way. This, a lot of them act like this, where the graph approaches the x-axis all the way to the right. Here's another example. The integral from 0 to 2 of 1 over x plus 1 squared. And here's the graph, and the red shaded area is what I'm trying to find. The reason that this one is improper is because it has what's called an infinite discontinuity, which basically means a vertical asymptote. This graph, if I were to trace the graph this way, it has a discontinuity because I can't continue drawing this graph without picking up my pencil and moving to the other side of the asymptote and drawing the rest of the graph. So to find that area, we're going to have to use an improper integral. And anytime possible, I want to use symmetry. So I know that whatever the area is, it's double the area from 0 to 1, since this graph is symmetrical about x equals 1. So although my book doesn't do it this way, we're going to use a little shortcut and just do from 0 to 1. And then I'll double that, and we'll get our final area. And if that area turns out to be infinity, then that's just going to be double that, which is still infinity. But one of two options. Either I accumulate all of this area here, and it adds up to a finite amount like the last one did, or it adds up to an infinite amount, which some do. Okay, so let's just forget about the two parts and just go from 0 to 1. Now 0 is fine. My function is defined at 0. I can plug it in. It's a real number. My function is not defined at 1. So what I'm going to have to do, again, is do a limit as b goes to infinity from 0 to b. Okay, and it's just, like I said, it's just to be politically correct. It's an annoyance that you have to write it, because when you evaluate the limit at the end, you're just going to substitute in b anyway. So why not just leave it as infinity and then substitute it in? And it's just a matter of writing something inaccurate through all the steps. And I would just, as far as I'm concerned, we could just leave the infinity there, but you never know when somebody's going to want you to write it the right way, so I've got to teach you the right way. Okay, so now we just worry about the integral. I have 1 over x minus 1 squared, and that's just going to be a u du situation. Okay, my u is going to be x minus 1, my du is 1, so I end up with u to the negative 2. My du is already there, it's perfect. So don't forget my limit, but my integral of u to the negative 2 is u to the negative 1 over negative 1. So that's going to end up being negative 1 over x minus 1. Make sure you agree with that. That's what I did there. Let me show you to the side. The integral of u to the negative 2 du is u to the negative 1 over negative 1. So that negative 1 on the bottom, I actually moved to the top, and then I moved the u to the negative 1 back to the bottom to make the exponent positive. Okay, and so now I want to substitute in b and 0. Remember, I'm substituting in for x. The limit as b goes to infinity. When I substitute in b, I get negative 1 over b minus 1. And when I substitute in 0, I get negative 1 over negative 1. Okay, and this minus here, it's because I plug in the top number and then plug in the bottom number and subtract the 2. Okay, so now let's evaluate this. As b gets really, 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 really big, I end up with negative 1 over, let's see, I'm evaluating, oh, I just realized my mistake. I'm going to have to go back through here and fix these. Go back and fix this starting right here. B is not going to infinity. B is going to 1. My mistake. A lot of times it goes to infinity, so out of habit I put infinity. Really, B is approaching 1. And technically it's approaching 1 from the left side, so I should put a 1 minus, say that I'm plugging in numbers slightly smaller than 1. Okay, and one more to fix. I don't know if I've told you this, but I only make mistakes like this to try to catch you slipping, so shame on you if you didn't get it. So I'm plugging in numbers slightly smaller than 1. When that happens, this first part becomes something like negative 1 over, let's just use 0.99. 0.99 minus 1 is negative 0.01. I'll plug in 0.999, then it's 0.001. One way or the other, it's negative 1 over a tiny negative number. And then the other part's just a positive 1. As b gets closer and closer to 1, negative 1 over b minus 1 gets closer and closer and closer to infinity. Okay, this right here is approaching infinity. It's positive because the top and bottom are both negative, and it is infinity because it's 1 over a tiny number. Okay, so long story short, that area is infinity. The area from 0 to 1, just this half here, all the way up, is infinite amount of area. Okay, so if I throw the other side on, if I double that infinity, I still get infinity as my answer. Okay, so the word that we will use there is that this integral diverges, meaning it never stops getting bigger. If I follow that area all the way up, 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 up for huge y values, I will just keep adding on. It's not going to narrow out at any value. So that one area that I used the calculator for, that never got above 1. Just pick a number, 88,000. Eventually, I will accumulate 88,000 worth of area in between these two green lines. Pick another number, 2.8 million. Eventually, I will get to 2.8 million. That's what it means to diverge. You can't pick a number that this area will not eventually reach. Okay, so that about wraps it up. Just want to mention again the tricky part. Finding this limit right here. Those you may have done in the past, you might have breezed through them really quickly, but these limits at asymptotes really are a big focus for this section. Okay, so that wraps up really all the notes for this entire chapter. I will see you in class on Wednesday. Have a good one. Young out.